Thanks everyone for being here today. I'm going to talk about the response by words that are not creation, majorly fairness and ranking. I'm going to talk especially about exposed fairness and individual exposed group fairness and individual fairness and ranking. It's okay. Today, the agenda for today is going to be as follows. First, I'm going to motivate fairness and ranking. Then I'm going to introduce some preliminaries to look at fairness in ranking. And I'm going to talk about 3 of my recent works about fairness in ranking. So let's go ahead with the motivation. We see rankings in many real-world applications such as Google search or the Netflix recommendation or our Instagram and Twitter feeds. Sometimes we also see applications where we are ranking people in real world. Hence, it is important for us to look at the fairness considerations of rankings. We also know that many machine learning models are biased against people. For example, the Compass tool is known to predict disproportionately higher recidivism scores. The score which says what is the probability that the person is going to reoffend if released. And this score is disproportionately higher for African American defendants compared to other races. In the figure shown here, the false positive rates for the Black defendants is almost twice as high as that for the white defendants. Similar observations have been made in the literature. For example, a comprehensive report by NIST has established racial discrimination in face recognition technology. There are a lot more questions here. How does the data get biased, or how is the bias even observed, and what is considered unfair? What are the incompatibilities between different fairness notions? There are lots of such questions, and there are these excellent surveys and lots of recent work studying similar problems. You can look at any of these things if you're interested. I would particularly look at this example where, let's say there are a set of students and the students are being ranked for the sake of college admissions. Now, a straightforward way to do it is to look at some of the student features such as test scores, high school GPAs, and maybe some of their demographic features. And different functions of these features are going to give us a different ranking as shown in the second table here. So an algorithm or a pre-decided set of rules gives us a scoring function, which is a function of the features. Now, the question is a score-based ranking always going to be fair? We know that some of these features are not going to have fair scores. Therefore, the ranking that is defined based on the scores may not be fair as well. So our goal is to either in process for fairness in the scoring function, that is to learn a scoring function such that it mitigates the bias in the scores and outputs of fair ranking, or to post-process the output of the scoring function as to satisfy fairness constraints. So I'm going to talk more about in-processing and post-processing in this talk. So that's our motivation. Let's look at some preliminaries for fair ranking. So whenever I say ranking, I look at it as these two views. On the left-hand side, I'm looking at it as a matching problem, where bipartite matching problem, where on the left-hand side, I have the items, and on the right-hand side, I have ranks. And each item is assigned to exactly one rank, and each rank is assigned exactly one item. But we can also think of it as the 0-1 rank assignment matrix R, where the rows are items and the columns are ranks. So each row has sums to 1 and each column sums to 1. Hence, this is a stochastic matrix. Apart from the ranking, we are given some relevance scores for the items. Here I'm calling it row 1 to row 9 for the items 1 to 9. And we also have position discounts corresponding to the ranks, here V1 to V9. In general, the assumption is that the position discounts are non-increasing with the ranks. So then the ranking utility can be defined as rho transpose RV. This is one form of ranking utility, and discounted cumulative gain is a popularly studied notion of utility in ranking, where the position discounts are of the form 1 over log 1 plus j for rank j. You could also define precision at k in the same form. Apart from the relevance scores, position discounts, I will also look at the groups that the items can belong to. Specifically, I'm saying that the items can belong to disjoint groups. For example, in this example, the items here can belong to groups male and female. And I'm going to particularly look at the representation of these groups. That is, the number of items in the top 4 ranks from the group male is 3 and the group female is 1. This is what I'm going to call representation, and I'm going to define my fairness constraints based on the representation of the groups in the ranks. So before that, I'll define what is called a block of ranks. A block of size k is a set of consecutive ranks I to I plus k for some I. Here, the shaded region is a block of ranks from I to I plus k, for k is equal to 4. And if you think of groups as this diamonds and clubs, in this block, there are 3 items from diamond group and 1 item from the clubs group. And now the number of items from a group in a block is defined as a representation of the group in that block. So based on these representations, I'm going to define the group fairness constraints as the lower and upper bounds on the group representations in ranks I to I plus k. So in this example, I have a lower bound on 1 and upper bound of k by 2 on the diamond group. Since k is 4, the upper bound is going to be 2. According to these constraints, this block is not fair because it violates the upper bound constraint on the diamond group. But this is when we say the block is fair, but when do we say that a ranking is fair? Okay, before that, so these kind of notions were also studied in classification problems, matching problems, knapsack, and selection problems. But for the first time, Zelike et al. 2017 and Sellis et al. 2018 have introduced these kind of constraints, representation-based group fairness constraints, in the context of ranking. And this includes equal representation, proportional representation, or the 4/5 rule or Rooney rules, and so far can be modeled in these kind of lower and upper bound constraints on the representation of the groups. So we can have such constraints in blocks where blocks are all k consecutive ranks as shown in the first row. Here, for each 3 consecutive ranks, we can ask for our ranking to be fair. You can think of the application where you're scrolling through, let's say, an Instagram feed, and you want each window to be fair. It could also be fair. You could also ask for fairness in all prefixes, which was introduced in Sellis et al., where the block sizes vary, but they always start from 1. It could also be like the top right, it could be the disjoint blocks. It can arise in the context of Google search results, where you see the first 10 pages and then the next 10 pages. So that is captured by this figure here. Or you could also just ask for any subset of these blocks to be fair. More importantly, we can define both group and individual fairness in terms of these blocks. So for group fairness, we said that we want the representation to be between some lower and upper bounds for certain group. But in case of individual fairness, we will ask for the probability that an item is in a particular block to be between certain lower and upper bound on the probability. So those are the constraints that we would look at in this talk. So there are other notions of fairness in ranking as well, like fairness of exposure, where the representation being between lower and upper bounds is not the thing that is measured, but instead it asks for the groups to have equal exposure, where exposure is defined based on the position discount I talked about. So if rank 1 has a exposure of 100 or equivalently position discount of 100, and rank 2 has a position discount of 90, then a group that is being ranked at rank 1 is getting more exposure than that is being ranked at rank 2. Therefore, in the top K ranks, we can ask for equality of exposure for different groups. And also for individual fairness, there are popularly studied similarity-based fairness notions, but we will look at probabilistic individual fairness in blocks that I just talked about. Let's consider this example where we have a set of items and there's a recruitment portal. And whenever a recruiter asks the recruitment portal to give a ranked set of candidates, it is going to show a ranking of the items that it has. And we assume that the items can be divided into disjoint groups. And there are also certain predefined fairness constraints on each of these groups in the top K ranks. Now, in cases where, let's say, Bob and Alice are two individuals here, and they have very similar skills. Let's say one has a relevance of rho and another has a relevance of rho minus epsilon. Then one is always going to be ranked below the other if we were to output a deterministic fair ranking, even after imposing fairness constraints. So we propose to use randomized fair rankings instead, so that we don't systematically discriminate against certain individuals. So in fair randomized ranking, every time we need to output a ranking, we do so by sampling a ranking from the distribution or all possible rankings. So here we could ask for ex-ante guarantees or ex-post guarantees, where ex-ante fairness is satisfied in expectation. This is applicable in case in low stake applications such as YouTube recommendation systems, or when items are very frequently being ranked, so guarantees and expectations are sufficient. We could also ask for ex post fairness. That is, we can ask for fairness to be satisfied after the fact. This is mainly applicable when fairness is legally enforced. Ex-ante can be satisfied for equal representation in this example, even when all the items in a ranking sample belong to the same group, like the example I have showed. Whereas to satisfy ex post fairness, you would have to output each ranking that is satisfying fairness. Okay, so again, like I said in the beginning, there are two ways of achieving fairness. So one is via in-processing. That is, we are given features as input. We can train a neural network with a utility and a fairness error. And after training, we can take whatever output it gives to be a fair ranking. But we could also train a neural network without fairness, just for utility, and take its ranked list, whatever the output it is giving you as the ranking, and then apply re-ranking algorithms to get a fair ranking. The first kind is called in-processing, and the second kind is called post-processing. So I'm going to talk about both the algorithms that we have proposed to achieve fairness in ranking. But in summary, the problem is as follows. Given a set of n items, we want to order them or some of them such that some notion of utility is maximized, while some fairness constraints are satisfied. So we are going to look at these 4 points while we go through the papers. The first thing is the constraints, that are the constraints on groups or on the individuals, and whether you want the output to be a deterministic ranking or a randomized ranking, and whether you want the effect of the output to be ex post or ex ante, the fairness, and whether you can do in processing or post processing. Let me talk about the first work. So this is a joint work with Amit Deshpande from Microsoft Research Bangalore, and Anand Lewis is my PhD supervisor at IISc, and this has appeared in ICHKAI 2023. So this is going to be about group fair randomized post-processing algorithm which satisfies ex post fairness. So like I said, the scores could be biased in the student example, and hence the rankings could be biased. So previous works have tried to model these uncertainties or biases in the scores and then come up with fair rankings. So assuming uncertainty in scores, Singh et al. 2021 gave an individually fair randomized ranking algorithm, and assuming the implicit bias model on the scores, Sellis et al. 2020 gave a group fair deterministic ranking algorithms. Both of these assume something about the uncertainty or the model of the bias. But human biases may not be of such simple forms, and we know that machine learning models may exacerbate such biases. So it's hard to model these biases. So we ask for achieving fairness in rankings when we cannot rely on intergroup comparisons. That is, we assume that let's say we have these scores, and within a group, we can just look at the ordering based on the scores, but we do not compare the items across the groups based on the scores. Like a 7 in a group 1 may not be the same as a 7 in a group 2. So if you completely ignore these items, then how do you merge these group-wise rankings? So some useful notation here is as follows. Let me define a tuple x1 to xl, where L is a number of groups. And this is an integer tuple where xj is an integer that represents the number of top k ranks assigned to group j. Therefore, the sum of the coordinates in x is going to be equal to k. Now, I will only look at those tuples which satisfy the representation constraints on the groups. And I'm calling this a set of group fair representations, calligraphic X. And for each corresponding X, I'm going to have a group assignment. That is, after I know how many items should go to the top K rank from a particular group, I still don't know which ranks particularly should go to that group. So these are all the permutations of X possible. And I'm going to call them the set of group fair assignments for X. We now propose an axiomatic way of achieving ex post group fairness in rankings, especially when we rely on comparisons of the items within the group and do not rely on comparisons of items across the groups. So because we rely on the intra-group comparisons, we just want that the in-group consistency to be satisfied, as in items belong in the same group will always appear in the ranking according to their true scores. And because we do not rely on intergroup comparisons, we ask for representation fairness. That is, all non-group fair representations should not be sampled, and all group fair representations should be sampled uniformly at random. For example, the calligraphic X is what I talked about just now. These are all the set of group fair representations, and any integer point in this set has to be sampled with equal probability, and anything outside shouldn't be sampled at all. And this, and after sampling this, you're going to take a permutation. So ex post fairness is always going to be satisfied. However, if you just sample any permutation that is going to sample this 2, 3, 1, 4, for example, you can still always rank one group at the bottom of the top K. So to avoid that, we also ask for ranking fairness, which is defined as follows. So given a prefix of the ranking. So here, let's say the prefix is 1 and 2. That is, first rank is assigned to group 1, second rank is assigned to group 2. Then the third and fourth ranks being assigned to group 1 and group 4 should be equally likely. It can be either 1 and 4 or 4 and 1. So this ensures that you don't systematically discriminate against one group in your top K. So for these three axioms, we show that there is a unique distribution that satisfies all of them. You can sample from this distribution as follows. So you just first sample an integer point uniformly at random from X, and then you sample a permutation Y given X uniformly at random, and then assign items to the ranks while maintaining the true order within the group. So steps 2 and 3 are easy, but the first step is non-trivial. And we are going to look at algorithms to sample these points uniformly at random. There are also some other guarantees that can be satisfied. In the interest of time, I'm going to skip this. So yeah, how do you sample integer points from the set of group fair representations? So first, let's look at the convex hull of X, which I'm calling K. And let's scale the polytope K by a factor 1 plus square root L over delta. L is the number of groups, and I'm going to show what delta is. So the algorithm is as follows. We first sample a rational point Z uniformly at random from the scaled polytope. So there are several recent works that have proposed algorithms to do this efficiently. Cousins and Mempala 2018 has, I think, is the state-of-the-art algorithm to do this. So you won't get an exactly uniformly random point. You'll get a point at the total variation distance of epsilon from uniform distribution. So just sample a rational point Z, but we want an integer point. So we round it to an integer point using this very simple deterministic rounding algorithm. Now, if the integer point falls inside K, we accept it. Otherwise, we reject and we go to step 1 again. So delta is going to be the radius of the ball inside K. So which is defined using the parameters of the problem as follows. And if delta is at least L to the 1.5, we get that the probability of acceptance is at least a constant. So therefore, our theoretical result is as follows. For any constant epsilon that satisfies these things, our algorithm samples from a distribution that is also at a total variation distance of epsilon from the uniform distribution in polynomial time. So the main thing to notice here is that Kannan and Vempala 1997 have also come up with a very similar algorithm, but they actually solve it for polytopes in general. Our polytope is very specific. We have this rectangular or box-like constraints cut with a hyperplane, but Kannan and Vempala 97 works for any general polytope. But they need a ball of radius L to the 1.5 square root log L to be inside the polytope. What this means is that their algorithm runs in polynomial time for smaller set of fairness constraints, but both the algorithms will essentially run, but may take exponential time. So we also give an exact algorithm based on dynamic programming. I'm not going to go into the details of this, but you can think about counting the number of feasible 0-1 solutions for an abstract problem, and a very simple extension of that is going to give you the recursion in the count step. And then the sampling step is also fairly straightforward. So Stefankovich 2012 has have proposed this similar DP for counting 0-1 abstract solutions. In summary, a random walk-based algorithm has order K square, L square, running time and expectation. Our dynamic programming, although it's order K square L, in practice, our random walk runs faster. Also, we show that using Barvinok 2017 and Park 2000, you can get an L to the order L, order log square K algorithm to sample exactly as well. But of course, this is an exponential dependence on L. And in some very specific cases, even a brute force algorithm is going to give you a polynomial time algorithm. So these are some of the experimental results. I think the running time is the most important here. The random walk, as you can see, as the rightmost plot, the orange one is a random walk and the purple one is the DP. So as k increases, our random walk is indeed faster than the DP. And this first and the second plots just show that the fairness is satisfied as guaranteed by our algorithm. So like I said, we achieve fairness of representation of the groups, and some of the future directions can be how to achieve fairness sensitive to the exposure of the ranks. And also we completely ignored the intergroup comparisons, but maybe it's nice to look at how to use the intergroup comparisons with at least some confidence. And our code is open sourced at this link.
There's one use case where this can be applied. In Texas, for example, there is some rule that for college admissions to the UT system, there is some percentage X that floats year after year, but now it will be 8%. If you're in the top X% of your public school, you're guaranteed admission to one of the UTs. Right?
I heard that they went to get rid of the system. Yeah, because they used to have it in other Texas schools, but not anymore.
So then what is the problem? Everybody in the top some 8% is going to be admitted.
But the question is, yeah, so there is a lower bound of saying 8%. The upper bound is lower. And you can compare the page, say, different states, for example, for the resources.
Yeah.
Yeah.
Yeah, actually, another application is of this work is to use it to train a fair learning to rank model. When I say learning to rank, it's essentially the in-processing that I talked about. You're given features, you want to train a neural network using utility and all your fairness constraints, such that after training, whatever ranking it gives you is going to be fair. So there are no known algorithms to train a ranking model that incorporates ex-post fairness. There have been works that achieve ex-ante fairness, but this is the first to the best of our knowledge, to achieve ex-post fairness. So let's see how to do that. And this is one of the recent works. This is a joint work again with Amit and Anand, and also Ishan Bhansali. He was an undergrad at UC Berkeley. He's right now a PhD student at Wisconsin-Madison. So we study this under the Plackett-Lewis ranking model. This has been a popular LTR model in the recent times. Singh and Yorkins 2018 proposed to train the PL model via policy gradients for both utility and fairness, but that fairness is ex-ante fairness. And Oosterhuis 2022 in SIGIR recently gave an efficient sampling algorithm to train a PL model for some commonly used ranking utility functions and fairness measures. Again, all the existing works only do either in-processing for fairness ex-ante or post-processing for fairness ex-post. We propose an algorithm that does in-processing method for fairness ex-post. So the PL model and the training is as follows. So you're given features, the model predicts some relevant scores, and then you sample some rankings from the Plackett-Lewis model as shown on the right-hand side. And you compute the expected ranking utility, and you take the gradients of this measure and train the neural network via stochastic gradient descent. We propose to do the following sampling instead. We sample rankings that are only fair. So the way to do this is to first sample a group assignment using our previous algorithm, and then within the group do a Plackett-Lewis model. So Plackett-Lewis is like a softmax sampling, so you can efficiently compute gradients. And so that takes care of the product term to compute the gradients. And the sampling algorithm for the group assignment, it does not depend on the scores. So for the total, you can easily compute the gradients for the expected relevance metric. Therefore, we can again train the neural network via stochastic gradient descent. And the time taken to compute the gradient for n items in L disjoint groups, let's say you're taking m samples of the top k rankings, is in the PL gradient estimation is the term I'm showing here. And this is with the fastest algorithm that is proposed by Oosterhuis 2022. And our algorithm that we call group fair PL takes slightly longer time. Moreover, we show that when we assume that there is implicit bias in the data, or we inject implicit bias in the data, then our algorithm achieves higher latent ranking utility than just doing post-processing. So here the bias model is as follows. For a particular group, minority group, if the observed score is W observed, we multiply it by a factor of beta, which is less than 1, and then train the model on the biased scores. So in this case, let's say PL rank 3 true is the one which is trained on the true scores, and PL rank 3 is the one, the Plackett-Luce ranking model, which is trained on the observed scores with the bias. The next two, PL rank 3 plus GDL 22 and GAK 19, these are post-processing algorithms. That is, you train a Plackett-Luce ranking model and you take the output ranking and you post-process. And the final one is our group fair PL model, where we achieve fairness doing in processing. So what we observe is that whether there is bias or even when there is not bias, doing post-processing is not a great idea, because you lose something in terms of the utility compared to what we achieve by doing in processing for fairness. So this is the first plot, in the NDCG plot. In the top row, in both the plots, we see that the green line and the blue line are slightly lower than the yellow. Yellow is a gold standard. And purple one is getting as high utility as the yellow one. And the second plot just says that the fairness is also satisfied. The lines just have to be between the lower and upper bounds. So in summary, doing in processing for fairness seems to be a better idea than doing post-processing for the learning to rank models. Although we don't have anything theoretical to say about this, I think that's a nice, interesting direction to look about. Again, here we have completely ignored the intergroup comparisons. Maybe we can think about using it with some confidence, but here again, you're go into the problem of finding gradients, and it may not be very easy to find gradients in this case. And lastly, I'm going to talk about one of our recent works, which is sampling individually fair rankings that are always group fair. By always, I mean exposed group fair. So here the constraints are both on groups and individuals, and the output is going to be randomized ranking with an effect of exposed fairness. And this is again going to be a post-processing algorithm. So I have talked about ranking being 0-1 stochastic matrix, but when you look at this distribution of over rankings, you can think of this fractional matrix, which is also a stochastic matrix. That is, the rows sum to 1 and the columns sum to 1. I'm calling it D in this case. So Dij represents the probability of assigning item I to rank J.
Make a small unit, that's called a doubly stochastic, because the rows are columns.
Yeah. I thought doubly stochastic is called stochastic also.
No, stochastic just means, for example, column sensitive.
Okay. Yeah. So yeah. So let me talk about the next one actually. So we can also solve linear programming linear programs to maximize ranking utility, that is rho transpose dv, while satisfying group fairness and individual fairness constraints. But the question is how to round this LP solution. So seeing Kempe Joachim's 2021 used Birkhoff-von-Neumann rounding to round the fractional LP solution, but they only have individual fairness constraints, not the group fairness constraints. So the problem with having group fairness constraints also is that the resultant polytope can have fractional vertices, and we don't know how to decompose this using, we can't use Birkhoff-von-Neumann decompositions on this. So therefore, we studied this problem, but we study it in a slightly different setting, as in we ask for group fairness constraints in disjoint blocks. So the blocks cannot be overlapping. Our algorithm works only if the blocks are disjoint, and the groups are also disjoint, or they can be any coming from any laminar set of constraints as well. So again, now the question is, you can solve this LP, but how do you round it? I'm going to give a short overview of this problem. So like I said, the group fair ranking polytope can have fractional vertices, but we know that from Nasre, Nimborkar and Pooler 2019 that the group fair bipartite matching polytope has all integer vertices. So here is our algorithm. We first solve the ranking LP and map it to a fractional bipartite matching space. So in this example, if the fractional solution of the LP is the one showed, so then the blocks, the first block is for the ranks 1 and 2, the second block is for the ranks 3 and 4, and there are 4 items. I'm going to first compute the projection onto the matching space, which is nothing but just taking the sum of the probabilities within the block. And we use the Panda, Nimborkar, and Lewis 2022 algorithm to decompose this fractional matching into integer matchings that are always fair. Now, how do you go back to the ranking? That we just do by ordering the items based on their relevance scores. So yeah, that's our algorithm. So for example, here, I can't use my card. So in the matching decompositions, the first one says 1001, 1001, right? So that means first item and the third item are assigned to the block 1. Now, how do you decide which item goes to rank 1 and rank 2? That we just define based on their relevance score ordering. So this ensures that the individual and group fairness are both preserved. But in terms of the ranking objective, we lose a factor of this alpha. But our experimental results show that we lose at most 6% of the utility by doing this on the real world data sets we have considered. So yeah, future directions are to maybe find better approximation algorithms. And throughout the talk, I looked at ex post fairness, but this may be very strict for some applications. So maybe it is nice to think about something in between ex post and ex-ante group fairness. So these are some of my collaborators, and yeah, I worked with Kishan also when he was interning at MSR. And yeah, my research is supported by Google Research, by the Google PhD Fellowship Program. And yeah, thank you so much.
Plenty of time for questions.
Okay, yeah.
Any questions? So what if you can approximate, you can violate the LJ and LJ, what happens?
Yeah, so we did not study that the randomized ranking setting. But what we did in another paper is that we studied deterministic ranking algorithms. But why we would violate the group fairness constraints is because we wanted to actually look at how much an individual also loses in terms of what would have been their true rank and what is their rank after re-ranking for group fairness. Look at the ratios of the group fair rank versus the true rank. So in that case, we have guarantees where we lose a little bit in the group fairness on the lower and upper bounds, and we get almost close to the guarantees for this ratio as well, worst case ratio. So doing it in these blocks kind of helps rather than having prefixes. So the same algorithm that the sampling algorithm that I talked about, we tried to do this for prefixes also, but it was very hard. We couldn't get anything.
Other questions? So some people here, when you're involved in the group, when John and so on, when some of the demographic information can be probabilistically a little wrong. Were you involved in that?
I think you and Sayed.
I was not.
Oh, yeah, Sayed and so basically,
Yeah, you
yeah, not to know that.
What is that about?
Realistic fair.
yeah. Because group membership, you can sometimes infer, but often it's a predicted action. For example, race and renewals, you can guess from the zip code, but you can't infer it probability one kind of thing. That's very interesting. There is some small results in noise.
Yeah. Yeah. So yeah, I have seen these things in subset selection and ranking as well. So then, I don't remember the authors, but they ask for like a pack bound. So with high probability, whatever the sample you get for the group labels, you want to be fair with respect to the fairness constraint. You want to output a fair ranking that satisfies all the fairness constraints. Maybe the noise could be adversarial as well.
Can you tell us about some future directions you're looking?
So for future, there are a lot of open problems I talked about here as well that are interesting. But currently, I'm also working on the following problem. So let's say you don't have access to the scores of the items. That's what I talked about so far, that we have access or we can learn these features. But if we have an oracle access to pairwise comparisons of the items, then what can you say? So I'm currently studying a problem where I have this oracle access, and in the previous works, the goal was to be epsilon close to some best ranking. But if you do that, you might end up in a solution that may not be fair. You will still be close to epsilon close to the best ranking, but you may not be fair. I'm trying to look at query complexities to achieve fair rankings that are still epsilon close to the best.
Can I suggest a cool problem for people here that's only tangentially related to what you said, but it reminded me. So consider this problem. So you have n data items. There is an underlying total order on them, right? But you can only make pairwise comparisons because the data type may be some complicated data type, right? So it's expensive to just compare, right? But there is an underlying total order, and every time you ask a query between I and j, you return which comes before the other in that specific total order, right? And so you want to sort the items, right? Of course, if you make n choose to queries, you can sort it, right? So can you do better? Basically, it's a randomized algorithm with around n to the 3 halves very complex. By Sanjeev Khanna and Shilpa Khanna from maybe about 10 years ago. Yeah, it's interesting if you can do better.
To find the best ranking, like
no, this is just there is an underlying total order of items, and you want to find the total. You want to sort the items.
No error. You want to find
Yeah,
the exact ranking.
Yeah, but it's noisy also, that's interesting. But yeah, the query complexity can do much better than explained. But n to the 3 halves, it's not at all known. It's also interesting that in your case, we're looking at query complexity.
Yeah.
So you have some results of it, or you're planning to look at it?
No, I have some results, but I don't have matching bounds. I'm actually planning to submit to AI stats, but I don't know if that's going to happen.
Other questions? Thank you.
Yeah.
Thanks a lot for the talk.